All right. First thing I want to talk about before I talk about collisions here is how momentum and kinetic energy are related to each other. If you look at the equation for kinetic energy, and if you're an AP, this is just a K. IB, it's EK. You've got 1 half mv squared. Now, down here I wrote a little note that says, okay, well, if momentum is m times v, and I've got an m times v, but then I've got a squared. I can't take the square root because then I get the square root of m, and that's not in there, okay? So what I really need to do here is somehow get m squared into the equation. So what I'm going to do is multiply the top and the bottom by m, okay? And this is going to give me that ek would be equal to 1 half, and then we'd have m squared and v squared on the top. And instead of doing 1 half, I'm just going to put the 2 on the bottom with an m. Okay. Now, if m times v is p, then m squared times v squared is p squared. That's going to equal kinetic energy. Now, this is a fairly useful connection, especially in IB, but it is also particularly useful with your AP class. So if you understand that particular relationship, that's something you can use. Now, on IB, this is in your packet. I don't think it's on the AP packet. Okay. All right, so let's get into collisions. And I've written out the majority of it because it's kind of a pain in the butt to write. It's much easier now to sit through and talk about. So we're talking about all these collisions. The first type of collision that I've got down here is a perfectly elastic collision. The definition of the perfectly elastic collision is that kinetic energy and momentum are conserved. Okay, both things have to be conserved. A perfectly elastic collision is fairly rare, but in our ultimately, ideal universe that most of this physics course is designed for, this is what we're going to use. Okay, so I've also said perfectly elastic. What does elastic mean? Elastic means that they either bounce off or simply that they do not stick together. They do not become one mass. Okay, so I've written up a couple things. Kinetic energy before has to equal kinetic energy final. The Giancoli book likes to use a prime for final, or if you wanted to use naught and F, that works fine, or I and F, that works fine. For IB, EK, and I put I and F, it doesn't really make a difference. Just remember the energy before must equal the energy in the end. So if kinetic energies are supposed to be the same, then I've got some formulas here, and they're all the same thing, okay? But this says the kinetic energy of one object. Okay, so if we're talking about two objects colliding and bouncing off of each other, the kinetic energy of one object, 1 half m u squared, plus the kinetic energy of another object, 1 half m u b squared, must equal the kinetic energy in the end. So all that this equation says is if there's two objects with their own kinetic energy, then they must have the same kinetic energies in the end. But let's say one of them had a kinetic energy of 100 and the other one was at rest. Well, then in the end, maybe they're 50 and 50. Okay, now I don't want you to think that it's split evenly every time. It does depend on the mass, but that's a case where one of the things didn't have any kinetic energy, so it just went away. Okay, so one thing had kinetic energy, and now two things in the end have kinetic energy. That's possible. Now, again, the AP version up here, I've used V for initials and then V primes for finals. If you want to use VI over here and VF over here, I'm fine with that. For IB, they use U for the initial velocity and V for the finals. Again, it doesn't make a difference. The other part about perfectly elastic collisions that the momentums are the same. So again, you'll see that I have mv of A plus mv of B has to equal mv of A prime in the end, and mb or mvb in the prime in the end. Again, we're just accounting for the initial and final momentums being the same. Okay. One thing that I'm not going to go into detail on right now, but I think it's something that would be good for you to be able to see. This is a helpful little connection of the velocities before and after a one-dimensional collision. The proof of it is done on page 176 in your book. So if you want to take a look at it and see it, you can. I'm not going to go through it right now. Neither one of these things are actually in your equation sheet, but they might be helpful for solving problems. Okay, I'll leave it up there for a second. Okay, so let's talk about some other types of collisions. An inelastic collision. Well, if an elastic collision was things that stick together, inelastic collisions means if elastic collisions were things that don't stick together, then inelastic collisions are when objects do stick together. Okay. One thing that's a little different: momentum must be conserved, but in this case, kinetic energy is not. Now, that doesn't mean that energy is not conserved, just the kinetic energy. So I've written a generic formula right here. The kinetic energy initial equals the kinetic energy final plus other forms of energies, which actually means that these two things don't equal each other. There'd be something else. So if the kinetic energy was 100 joules, maybe you only get 50 joules here, and then 50 joules are other types of energy. And I've written down here that it's oftentimes heat, sound, or something else. Okay, but the momentums still have to be the same. So the difference between an elastic and an inelastic is in an inelastic that they stick together. Therefore, if I had a mass and a velocity and another mass and a velocity and they run into each other and stick, then the two masses become one and they share a common velocity. So I sometimes think about a tackle in football. You've got two guys running at each other. One of them wraps up and pulls the other one down to the ground. Well, after the collision, they share a velocity because they're connected. Okay, I wrote down here that this particular equation could be flipped around. This could be the initial velocity and these could be final velocities. If it was talking about an object that was moving together and then split apart, and oftentimes people just think this goes one way, you could really flip it to the other way. Okay. Last type of collision that I'm going to talk about is a recoil collision. If you look on here, it says collisions where the momentum before and after the collision equals 0. I always think about guns in this case, because if you're standing there and you're not shooting, if the gun itself is not, you haven't pressed the trigger yet, the momentum of you and the momentum of the bullet and the momentum of the gun is all 0. They have no velocity. But as soon as you pull that trigger, the bullet goes flying off in a direction. Well, that means the bullet must have a momentum. But conservation of momentum says whatever momentum we had in the beginning must be accounted for in the end. So if the bullet has a mass, which it does, and it's flying, then it has momentum. Well, what happens when you shoot a gun? Well, the gun goes the opposite way. Okay, so in this case, the momentum of the bullet is canceled by the momentum of the gun. Okay, this is also why you usually put the gun to your shoulder, so that not only does the gun have mass, but now you've also incorporated your mass. That makes the recoil of the gun much less severe. I actually always think it's funny. There's an episode of Tosh.0. They have a bunch of people shooting guns, and they're not like bracing themselves, and it's always a bunch of people shooting handguns, and then they hit themselves in the face because of the recoil. Obviously, if you increase the amount of mass behind it, or you're better prepared, that would be better than just kind of willy-nilly shooting it. Okay. All right, so those are the types of collisions: elastic, inelastic, and recoil. I want to go over kind of a helpful problem. This is a pretty common problem in physics called a ballistics pendulum. Sometimes helpful in trying to solve for, say, the initial or velocity of some sort of object. So if you've got a bullet, okay, and I shoot it into a block that's on a pendulum of some sort. Okay, if it's really heavy mass, the pendulum's going to rise up. It's going to increase its gravitational potential energy, so it'll come up to a height. So this is a helpful idea when kinetic energy is being turned into gravitational potential energy. Okay, so if we think about this, this is an inelastic collision. Well, the only thing moving to start And I'm going to do this with the IB variables, okay? The bullet has a mass and it has an initial velocity, that's u. When they collide, you're going to have the little mass plus the block mass, and they're going to share a velocity. Okay? This is our inelastic collision. Now, we do still have to have a conservation of energy, which in this case you'd have kinetic energy of the bullet, and then it would transfer into gravitational potential energy of the block and bullet combo. Okay, so once they run into each other, your kinetic energy would be 1/2 m plus big M, and their shared velocity would equal m plus big M gravity times height. Well, first thing you ought to notice is you got m and big M on both sides, so those go away. You would end up having 1/2 v squared on one side and g on the other. So I can bring the 2 up to the other side, and you end up with a velocity of 2gh. So if I take this up now, okay, and I substitute in for here, okay, this is a good way of finding the initial velocity. If I keep the u on one side and bring the m down to the other side, you're going to get m plus big M all over the little mass. I'm bringing this down, okay, and then I can plug that velocity in, which is 2gh, or square root of 2gh. And that can oftentimes be a good thing for the initial velocity of the bullet. Okay. One other thing that I just wanted to show real quick, and it's because I forgot to go over this with conservation of momentum. This is kind of the proof for conservation of momentum. If you've got two objects that run into each other, object B experiences a force produced by A. Object A experiences a force provided by B. Now, one thing that we should know, in collisions, those forces are equal and opposite. Okay, so if those forces are equal and they're in contact for the same amount of time, then I know that the change in momentum of A is equal to the change in momentum of B. Now, this is a fairly big concept, and especially in IB, they like to ask questions like, prove that the conservation of momentum is true based on Newton's laws. Well, in this case, if I have equal and opposite forces and they're in contact with each other for equal and opposite, well, not equal and opposite, but equal amounts of time, then if F is delta t, then the change in momentum of A must equal the change in momentum of B. So this is oftentimes useful. Not to mention, I got to draw a smiley face. Smiley face. All right, hopefully that's helpful.